All right, this is our third and final day of Chapter 8 notes, and we're going to talk about a couple of theorems, which are also known as different tests that we're going to be using. And we'll use more of these tests in Chapter 9. So a couple of days ago, we talked about those p integrals. So we know that the integral from 1 to infinity of dx over x squared converges because it's got that exponent p that's greater than 1. Remember, we can also say what it converges to. It converges to 1 over 2 minus 1. So it converges to 1. But the question is, well, what about the integral from 10 to infinity? Now, the constant here doesn't matter. But what about the integral from 10 to infinity of dx over x squared plus x? So one extra term in my denominator there. We want to compare the function 1 over x squared to 1 over x squared plus x. Which one of those is larger than the other? And you can figure this out by thinking about plugging numbers in. Like, say we plug in 2, 1 over 4 compared to 1 over 4 plus 2. 1 over 4 compared to 1 over 6. 1/4 is bigger than 1/6. And that should always happen, right? On this interval, we're plugging in positive numbers for x, right? 1 to infinity or 10 to infinity. So for any number, we'll say 10 to infinity, 1 over x squared will be bigger than 1 over x squared plus x. And again, that's because this larger denominator, having this plus x in there, which makes it larger than x squared, this larger denominator means smaller fraction overall. All right, so why are we comparing them? Because let's think about a graph then. This is going to be a very loose sketch of the graph. They're both rational graphs, right? So let's say they have branches. One of them is going to look something like this. The other one is going to be slightly above that, right? Which is which? Well, we just said that the 1 over x squared graph or equation is bigger than 1 over x squared plus x. So this must be 1 over x squared. And this must be 1 over x squared plus x. And remember, I was kind of saying if an infinite integral converges, it means that it must be decreasing fast enough that when you're adding up that infinite area, you're pretty much adding up 0 at some point. And so it does have a finite area. So if 1 over x squared decreases fast enough to converge, then 1 over x squared plus x, which is already smaller than 1 over x squared, it must also decrease fast enough. The visual for this is like you can think of this 1 over x squared graph. I think of converging as like pushing down on it. If the blue graph is converging fast enough, then the red graph must be converging as well. So the smaller function decreases fast enough. Therefore, the integral from 10 to infinity of dx over x squared plus x converges. Now, we don't know what it converges to because it's not a true p integral, but we at least know that it converges. All right, so what we just kind of loosely did was the direct comparison test. So this is a theorem, and it's important to know which function is on top and which function is on the bottom. So let's let f and g be continuous on the interval a to infinity, and both of them are greater than 0, so we don't have anything dipping into the negatives here. And g of x is bigger than f of x. Okay, so the integral from a to infinity of f of x dx converges if the integral of g of x dx converges. So what does that mean? Let's add to this graph a little bit. I'm not sure how much of that you have on there. So what this is saying is, let's see, g is on top. Let's draw in a little f graph. So f is something underneath. It doesn't really matter what shape f is. If g converges, then just like I did in that previous example, it's going to push down on f. F has to converge too. So basically another way to think of that is the smaller smaller than the known integral. I'm just going to write integral like that. Smaller than known integral. No, actually, sorry. Let's write it like this. Smaller than known convergent integral converges. Okay, so what am I saying? This smaller integral, this integral that's smaller than this one, if I know this one converges, that one's got to converge as well. All right. Go the other way. If the smaller integral diverges, then the bigger one must diverge as well. So now we're kind of going the opposite way, right? We're saying, all right, here's f. We know f is diverging. If g is already on top of f, so here's g. If f is pushing up, diverging, then g is also going to diverge. Now, diverging doesn't really mean pushing up, but it's just kind of a good visual to say this area is going to continue to get bigger, and so is g's. All right. So, So to kind of phrase that, I don't know if my phrasing helps or hurts, but the larger than known divergent integral diverges. But honestly, in my brain, I'm just kind of doing this this picture. I'm more of a graphing type person. All right, so what do we know? This is not a p integral, but can we compare it to a p integral? So I always write my comparison here. And what's required on the AP test? I haven't found any scoring guidelines that require you to show what you're comparing specifically like this, but I think it's a good habit to get into because they're not always explicit in what exactly they want to see. Okay, so I know that if I cut off the extra term, that's usually what I'm going to be comparing to. So if I cut that off for a minute, I'd be looking at 1 over x to the 2/4, or 1 over x to the 1/2. So however you want to think about it, you would be looking at the integral from 10 to infinity of dx over the 4th root of x squared. So in that case, p is really 1/2, 2/4, whatever. Does that integral converge or diverge? Well, if p is 1/2, remember anything less than or equal to 1 diverges. So this integral diverges. How does this integral compare to the integral in my problem? So I can just erase my little scribbled out part. Hopefully you didn't scribble it out. How do these two functions compare? Well, which one has the larger denominator? In this case, the larger denominator is on the left, the one that I knew about. So that means that that fraction is smaller overall. And if you get confused about that, just like plug a number in. So again, if I plug in 2, I get 1 over the 4th root of 4 compared to 1 over the 4th root of 4 minus 2. So 1 over the 4th root of 2. 1 over the 4th root of 4 is smaller than 1 over the 4th root of 2. Right? 1/4 is smaller than 1/2 if you want to take the 4th roots out. Okay, so if back to my picture, my smaller function, the one on the bottom is diverging, that's pushing up, that means the bigger function is going to diverge as well. Okay, so I would say that the integral from 10 to infinity of dx over the 4th root of x squared minus x diverges. I don't have to do any antiderivative or anything. I can just say diverges by direct comparison test. We can write DCT for this class because it's going to get annoying to keep writing out direct comparison tests. But on the AP test, obviously, please write it out. Okay, so diverges by direct comparison test. And as long as you're showing this work here, you can kind of stop there. My more formal response that I may or may not have in my homework is like diverges by DCT to direct comparison test to known divergent integral from 10 to infinity of, I would just say 1 over square root x dx. But I don't think that I really need that because as long as I'm clear of my work here. Okay, let's do another one. So here we have dx over x squared plus 6x plus 9. So 6x plus 9, since we're plugging in from 1 to infinity positive x values, that's definitely adding a positive value onto x squared. So I should first say, all right, let's compare it to 1 over x squared. Maybe you want to do the comparison step first. Compare 1 over x squared and 1 over x squared plus 6x plus 9. I think comparing it first might be kind of smart because sometimes you realize that the direct comparison test isn't going to work that way, and we'll go on to our other theorem. All right, anyway, which one is smaller? So the larger denominator is the smaller overall fraction. So x squared plus 6x plus 9 is larger denominator. That's smaller overall. All right. So what do I know about the integral from, I'm just going to match these bounds, 1 to infinity of 1 over x squared dx? I know that that converges because it's a p integral. P is equal to 2. If the larger function converges, then the area underneath the smaller function is also going to converge. So I know that this converges by direct comparison test. And I'm just going to say 2, the integral from 1 to infinity of dx over x squared. All right. Now the question, do we even have directions here? Sorry, we don't have directions, but the directions are just, do these integrals diverge or converge? It didn't ask me, or I'm saying that our instructions aren't asking to actually find the area, but if we know it converges, that means that we should be able to, in some way, figure out an integral for that, or figure out an actual area for that. Okay, but we're not going that far in these notes. What about this next one? So I see 1 over x squared minus x. I should compare it to, we're pretty much always trying to compare to a p integral. So I should compare it to the integral, sorry, I'll do my comparison first. I should compare it to 1 over x squared. 1 over x squared compared to 1 over x squared minus x. Now in this case, the smaller denominator is on the right. That means that the bigger fraction is on the right. So I know that the integral from 10 to infinity of dx over x squared, I know that converges. But that's the bottom function, right? Here's the bottom function, and here's the top function. All I know right now is that the bottom function is converging. Think of that as pushing down right now. If that's pushing down, is it pushing down on the blue function? No. So the fact that I know this converges doesn't actually tell me anything. And I don't want to make it like, I don't want to compare like 1 over x squared plus x because that's not a p integral. I don't know it converges or diverges just by looking at it. Okay, so what do we do? If DCT fails, we have to go to a second theorem. It's called the limit comparison test. All right, so what's the limit comparison test? If f and g are continuous on the interval a to infinity, and if the limit as x approaches infinity of the ratio f of x over g of x, if that equals L, meaning L is a number, if that equals L, some L between 0 and infinity, then the integral from a to infinity of f of x and the integral from a to infinity of g of x either both converge or both diverge. In other words, if you get a number, when you take the limit of this ratio, we may be doing some L'Hopital's here depending, then the two functions act together. Okay, how does that work? Well, how does it work, I'm not going to explain at the moment, but of course, there's another video. I always refer you to YouTube. You can get on YouTube and look at all kinds of stuff about this. But what are we talking about with this f over g? one of these functions we're going to know what the integral is. So for example, I know what that p integral does, it converges. And then one of them we're not going to know, like the original problem in C. And so you want to put your unknown function over your known function. And then that will be the ratio that we're looking at to see, does that limit come out to a number? If so, they act together. So if I get a number when I do this limit, which I think is going to be our next problem, yeah. So when we do this problem on the next page, if we get a number, we will know since this integral converges, then my unknown integral must converge as well. Okay, so let's check it out. So back to, before we get to D, back to our problem. So now this got erased on my paper. I don't know if it's erased on yours. So let's get back to this. We had dx over x squared minus x. All right, so our direct comparison failed. I'm just going to make a note of that. Direct comparison test failed. All right, I still want to look at, I still know about the integral from 10 to infinity of dx over x squared. I know that that converges. That's my known. My unknown is the actual problem itself. So we're told limit comparison test. Let me get this back up here. We're told to take the limit as x approaches infinity of our unknown over our known. So I'm going to get the dx out of there. So our 1 over x squared minus x, we're taking these out of the integral for a minute, because notice there's no integral in this expression here. 1 over x squared minus x over the known function, 1 over x squared. I want to take the limit as x approaches infinity of that. And do I get a number? Now, don't dive right into L'Hopital's or anything. Like, if you plug it in as is, you get 0 over 0. But work on it algebraically a little bit. So this could be, to get rid of the complex fraction, this could be rewritten as the limit as x approaches infinity of x squared over, why don't we make this x times x minus 1? So you are allowed to reduce in there. All right, and then the limit as x approaches infinity of x over x minus 1. Now, don't forget, I know we've done L'Hopital's, but don't forget, this is a rational expression and it's a tie, so we don't have to use L'Hopital's. We can just think about the horizontal asymptote when you're doing limits at infinity. The horizontal asymptote here is 1. All right, it's not the numerical value that's important, it's the fact that this is a number. That's our L, right? And what did our rule say? It said, if this limit comes out to L, which is just some number between 0 and infinity, then these two functions have to act together. So back to what we know. Our known function converges. Therefore, the integral from 10 to infinity of dx over x squared minus x also converges. I'm going to say it converges by limit comparison test. Again, write that out on the AP test, but I'm okay with you writing LCT. All right. What about example D? We've got the integral from 5 to infinity of dx over 4th root of x squared plus x. Okay, so this is similar. Did we have the same one or was it minus x? It was minus x in example A. Okay, so let's compare it first to 1 over 4th root of x squared. I don't even bother simplifying because it's easier to make the correct comparison when you're looking at it kind of on the same terms. The right side has a bigger denominator. It's a smaller overall fraction. Okay, so am I able to use this by direct comparison test or do I need to use limits? So let's see. The integral from 5 to infinity of 1 over 4th root of x squared, which is really just, dx, which is really just x to the 1/2 down there. P is 1/2. I know that that diverges. The problem is this is the function on top. If the function on top is diverging, think of that as pushing up. Again, not really pushing up, but just for our visual sake. that's not affecting the lower function at all. So I can't do direct comparison test, but this is my known and the original problem is my unknown. So I'll go over to limit comparison test and say, all right, the limit as x approaches infinity of my unknown over my known. So 1 over 4th root of x squared plus x divided by 1 over 4th root of x squared. Clean that up. So really we're looking at 4th root of x squared over 4th root of x squared plus x. All right, again, we don't need to go through L'Hopital's and all of that. This is a limit at infinity, and we're just thinking, hey, this is kind of rational, and it's a tie. These are both x to the 2/4, or x to the 1/2 as the highest degree there. So we can say that that divides out to 1 at its horizontal asymptote, which again is just a number. A lot of times you're going to get 1 because of the function that you pick. The times that I usually don't get 1 are if the original problem had some sort of coefficient, like a 2 or something in the numerator. Then I don't choose a 2 in my known integral, then maybe I'll have another number here. That's why it can be any number, but a lot of times you're going to get 1. Okay, anyway, so since I got a number, I know that these two functions act together. Let's make a note there, sorry. These two integrals act together. And in this one, they act together. So what does that mean? Well, the known integral diverges. That means that my unknown integral also diverges. So my final formal statement here is that this diverges by limit comparison test. Kind of an interesting fact down here. We know that the integral from 1 to infinity of 1 over x dx diverges, right? Because it's a p integral and p equals 1. Anything less than or equal to 1 is going to diverge. So what that's saying is the area under that curve never stops growing. Think of it this way. You can't paint that wall. You'd be painting forever, right? If I said paint the space under that curve from 1 to infinity, you would never stop. But if you rotate that around the x-axis, the volume that you get actually does converge. Think about rotating that. So if I rotate this around the x-axis, I get pi times r squared, so it becomes 1 over x squared. Then you get pi times something that converges, and you could actually get a volume that's finite. So it's interesting. It's like you can't paint the wall, but if you rotate it around the x-axis, you could fill up that little cone shape or funnel shape, I guess, that you get. You could fill it up with paint. It would have an end to it. So I just think that that's kind of crazy and interesting, and math is weird. Okay. Summary. We've had 3 days of notes just in this one section, and we're going to turn around and review and then have a test. So we have a lot of things to kind of think about in this chapter. Make sure that in this chapter, and really from here on out, that you're checking the interval, the limits of integration here. You're checking that for infinite discontinuities. Like, are there any values for which my function is not defined in here? If so, split it up. You may need to rewrite something as a limit at infinity or at the discontinuity. So if you do have an infinite discontinuity, or if you have one of your upper or lower limits are infinity or negative, you have to use limit notation. We're still using all of our integral techniques, so that's the reason that this chapter started off with just like, hey, let's just throw everything at you and try to remember when do you use u sub and when do you have an arctan or something like that. When you're using limits, you may have to use L'Hopital's if you're getting infinity over infinity or 0 over 0. And remember to show your limit as whatever a approaches infinity or x approaches infinity of f of x equals, we'll say 0, and you also have to show that that limit g of x equals 0, and then we say use L'Hopital. So remember, there's a formality there. When you're using your DCT or LCT, and when you're doing some of these infinite integrals, if your integral comes out to a number, then your integral converges. You get a finite answer. If not, if you get infinity or something that does not exist, then your integral diverges. Be on the lookout for p integrals. Remember, the upper limit has to be infinity for it to be a p integral. And again, sorry, I jumped the gun on my DCT, LCT. Down here, for a direct comparison test or a limit comparison test, you may just be answering, does this integral converge or diverge? If that's the case, that's great. You're just using those two tests to figure it out. If they want you to actually, if the integral converges and they want you to actually find the answer, they will say that in the directions. But if it just says converge or diverge, you're just using the tests and coming up with that conclusion. All right, so that is it for today. We will review tomorrow.